Hello everyone. Today I'm going to talk about the project 2 where we have to identify some two node network and perform the network reduction using the island method. And so here we have the data from the NASA where we have collected the journals and their respective author citation, and our objective is to find the relation between the journals and the author citation. What pattern does this show? That's what our whole objective in this analysis. The data was not easily available, so we had to do some sort of API registration with them to get the data. And after we got the data, we plan to identify the unique journals. We want to identify the unique authors, and then understand the degree of them, and then identify the edge weighted, and finally build out from there to check our analysis on them. So this is the edge list that you can see. We have journals and we have authors. So the journal Nature material is citing Jim AK and Novus Leo KS as an author, and then the Astronomy and Astrophysics is citing these two authors, and similarly. So this is a very high level view of the data set that is going we were going to use for our whole analysis. Then we are just actually storing up all the authors and the journals in a separate entity so that we can use it in the later stage. Now we're just going to plot a very high level graph with all this information just to see how does this look. This data set, this is the huge whole network, and you can see it's condensed, and we see some sort of somewhere it's very dense and somewhere it's very light. So we'll try to identify that pattern as we move ahead. So from the Gephi, we actually managed to get a better picture of this. Every green dot that you can see is actually a journal, and every red dots are actually the author. So this whatever journal is this is actually citing these people, and there are few people coming from this side, and there is all the green dots are journals. So we can see there are not too many journals, which can be counted maybe around 17 that we have in this data set, and there are like around 1600 plus authors in this. So this is a very condensed network here with everybody's all this journal is citing big set of authors, and then there is this set. So we'll try to understand this graph as we move ahead. Then adding now we want to just adding some node attributes so that we can better understand our graph when we have to actually analyze it. And we have added the bipartite parameter to our graph so that we can display the data in the right fashion. Okay, so as I said earlier, we have total 16 journal and total number of authors is 1662 in our data set, and we can easily list our all the journals here. And then the number of authors is this thing. So this is again a data set which we tried building based upon the eigenvector centrality of all the nodes in the network, irrespective of whether they are author or journal. But this is what we see, and if I have to actually name them, we see mostly these are the authors having very high eigenvector centrality. Okay, so this is a very high level information about the graphs that we created. It has these many nodes, and this is the average degree. To start, because this whole data set has two node in it, so we can very well say that it's a bipartite graph. But does this graph really shows that attribute? Let's check with the network X. So we can very easily see from the network X that yes, it is a bipartite graph because network X was able to identify the this graph. So in theory, bipartite graphs are the graphs which have two vertices, and you can very easily identify them or isolate them. Like in our case, it's journal and the authors. We are able to identify them, and a journal is not citing a journal, and an author is not citing an author. Only journal can cite an author. So it's like you within a set, you are not citing themselves, but you are citing someone from the other set of the vertices. So that's what the bipartite graph is. So we can very easily using the standard functions, we can easily identify the top and bottom nodes. There's like one set is on the top, one set is on the bottom. So and we will try to plot that graph. We are giving some green and red color for the one is used for the green and one is for our journals. So we are trying to put them color so that we can easily view them, and we are checking them in our graph. So this is our bipartite graph that's very clearly showing all the nodes that you see on the top. Most all are journal, and then in the bottom you have all the authors. These the size of the node says how impactful or how big the citation group is for these journals. Now we have done all this information, all this analysis. What one thing that was very easily identifiable, that this network is not connected. So when we say it's connected or not connected, it's simply like you cannot travel from one node to other node being part of this network. So there is always a gap, like some place you cannot, some nodes are completely disconnected. There is no path to at least one network or another. So to build a, find out the connected network within this, it's the process that we have to go through, identifying the different components in this graph, so that we can find out how many connected components are inside this complete network. And there are multiple ways that we can actually tackle this problem. We will try to see how we have done this. You can see that we have also run the analysis if this is a connected graph, it is a directed graph, or it is a bipartite. So the only true that we got from the network X is it's the bipartite graph, and rest everything is false. So once we perform our analysis, we'll be able to answer this, whether we'll be able to get a connected graph from our further checks. Now I'm actually creating a bipartite graph because it's a two node network. It makes more sense if we are able to view this data in a matrix form. So our objective is to present it into a matrix where one row of node one is the row and other node is a column, and you are able to view this utility matrix where you can identify their citation of the authors into the journal by like 1 and 0. So 1 means the author is cited by this journal, 0 means this author is never cited by this journal. So we'll try to find that information. So we use the different methods within the network X to get the adjacency matrix, and then convert it into finally a data set which can be easily translated into a matrix form. We also gave them the name so that we can further, because when you get this, you always get the IDs, you don't get the name from the adjacency matrix. So we had to give them the name so that we can better visualize our data. And you can see this is the matrix that's coming out. You can see like this particular, the Valley InterScience publication is not citing any of these authors, maybe in the head section. But if you see the physics physical review later is citing these four authors, at least we can see 111. So this journal is citing these many authors, and so on and so forth. Wherever you see 0, this means there is no citation. If you see 1, means that journal is being cited for this author. So journal is citing this author. So that's the overall visibility, and this actually helps anybody to view the complete network structure in one glance. Similarly, you can see here that like if I want to see how many authors are cited by this particular journal, I can very easily pass into the matrix and get the data. Okay, and if you see the below graph with the within from the Gephi, where you can see all these journals and the corresponding degrees, you can see in the second number is most talking about their degree. Now we will use the matrix data that we have collected so far, and we will try to reconstruct our graph, bipartite graph, just to again make sure that we still have the right data set, we did not lose anything. So I'm going to reconstruct that graph, and we are getting the our edges and authors and journals and data and everything. Again, I'm making sure this graph is connected. No, it's not connected. It is directed. No, it's not directed, and it is a bipartite. So we will be able to compute, build our graph, and then run our analysis on it. So before I actually plot the graph, I wanted to calculate the degree of each node, and so that we have the degree of each nodes. And then we also wanted to identify the bipartite attribute of this graph. So we created the final data frame where you have all the nodes and their degree and their bipartite, whether they are 1 indicates they are journal and 0 indicates they are author. So you are, like I have a new data frame where I'm able to identify each node by their degree and their type, whether they are journal or they are author. This will help me to build my plot my graph very effectively in the later stage. Now I'm actually calculating the edge weight. So this is actually an open point which we could have used any other method or any other way to calculate the edge weight, but we decided to use the degree of the node, both the nodes that those are that are connecting, like the degree of the author and the degree of the journal, and then multiply them. So we use a dot product of author's degree and the journal's degree to calculate the edge weight, and then analyze the complexity of the network by using this edge weight. So you can see here, this is my just edge list of the different edges that we have. Then we were able to calculate the final edge weight of this particular edge, and this information can be seen clearly here. And we actually applied this information in our further graphs. Now I'm creating a new graph that is called WG, just it's like a weighted edge graph I'm trying to create now, where I'm passing all this information that we have along with the edge weight. And again, I'm checking whether this graph is still bipartite. Yes, it is bipartite, and I'm able to see all this. You can see, like, if I have to check the natural materials, it is still citing GM and Novosilio. Then the edge weight is 2, which is what we have actually passed on here. So the data is there. Now we need to just start viewing this in the network structure. Here is the complete set of code where we are trying to realign our data and present it. Okay, so this is the graph, which is not different from what we have seen in the above slides, but this is pretty much the same, just to make sure the data is still right, but it has more information at this time, which we'll be able to present at the later stage. Our graph is still not connected. Now, this is the main part of the project where we need to identify what is the different connected components that we have in this network. So, so you can see this, like you can see there's so many chunks in this, but let's try to identify them. We are not able to name them. We can see all these journals names here, but let's use some method to identify these information. So the first thing that we need to identify is how many connected components are in this network. So to do that, there is a network X gives us the method that's identify the connected subgraph, connected component subgraph, where you pass on the graph and you get the information. Here I have passed G, but it's just the it's the same result that we will get, because also here I'm using WG. So it's just like a two different data set, but the result is same. So you can see we have total 11 subgraphs, connected subgraphs in this whole network. And if you remember, we had around 16 journals. So 16 journals and 11 subgraphs. So this is like there are like around four or two. There is some sort of overlapping. Maybe there. So in some subgraphs, we will have more than one journal at least. So let's try to find out which that subgraph can be. So we use this identified this length so that I can see what are the size of those different subgraphs. We can see I'm using WG, that's my weighted graph, and you can see 3 is the size, 29, and so on and so forth. So we see like 1308 and 312. Those are the two different connected graphs that we have in our network, and those are having size of 312 and 1308, and the other like 3 of size 29, and so on and so forth. So let's try to see them visually. If you go to the Gephi and if you are able to see this picture, like, and if you count, this is the exactly 11 in count. It starts from 0 and you can see the max is 10. So this is total 11 components that we can very clearly see on the Gephi side. And I think this would be my 1308, and no, this would be my this one. Yeah, 1308, and this should be my 3112. And why I'm saying this, because this is very condensed, so many authors, and I think they are centered around one journal. Whereas this looks like connected with at least one, two, three, four, maybe five. Let's see if we can further understand this network. And rest all looks very small, isolated networks. subgraphs within the network. So this is a very good interpretation of our how the components are connected, and so we can very easily move ahead from this stage now. And also, if you see this information here, so I have a component 0 of size 3 and so on and so forth. And yeah, see, this makes more easy thing. So our 312 is the only graph that has some differences in their maximum and the minimum edge. So I'm actually listing their maximum and the minimum edge weight, and you can see mostly everybody has the same edge weight, but this network connected network has a different edge weight, whereas the highest 1308 has the minimum edge weight of 1307 and the maximum. They both are the same. So it means that there is it is very highly unlikely that it will have another journal within this network, because they are, even if there, we cannot make any sense out of this. If we drop any of those networks, we may not be able to get any information. So we want to further analyze this network and see how this data looks. So just to read, this indicates that we can't find island in any component except component 3 at index 2. Rest all have the same edge weight and may go off the water level if dropped from the network. So if we have to drop edge weight of 1307, we would completely lose visibility of whatever is there in the component 5, because they just have only one edge weight. Okay, so let's further analyze the network that is of size 312, and we can very well see that the size is 312, and the most important thing, this is a connected graph. So this proves one of our point that yes, it is a connected graph, and the earlier the main graph was not a connected graph. We can very easily see that. Now we are putting some information here, again adding up the edge weight and everything, just to see. um, this is the method that we have used for the island method calculation. I'm using my edge weights to perform all the operation where we will compare the edge weights of the other edges in order within the network to segregate or drop the net edges. So here I'm calling my island method, passing my data. This data is nothing but the data that we have got from here. That's of 312 size, and I'm passing the iteration as 3. So once I see my output, I can very clearly see that I have a threshold of size of 2, and it is returning me no 311 nodes and just having one connection. So what does it mean? That if the links value with the true, if the edge weight of 2 is dropped from the network is only going to give me one complete connected network. We will lose the information about the networks that was connected with 2, because this will be an isolated node completely, and it's because there are not too many edges uh, forming this type of network. So we will completely lose the information about this particular journal, which is actually built connecting to this edge and forming the network there. So since the degree of 2 does not have much impact, as these may be group of authors that communicate repeatedly and thus have developed some kind of relationship, that's why, because it's not a big chunk of information that we are losing if we're dropping this information from the network. So that's why we can very safely say that these are like very small set of people um, just favoring each other in terms of citing the work. That can be just a safer conclusion to make here. Okay, if one thing that we note, that if we keep dropping the weighted edges, the number of graphs remains of the same size. So, and so this means that only the feature that represents the graph can be achieved by the 5 nodes of the edges. Like we can get the complete information about the graph if we need to focus. So maybe we know what are these nodes are. Maybe we can get the more information about the complete network or complete this subgraph by these 5 people. Okay, so now my objective is to plot this information into a graph so that I can clearly identify some of more crucial information about this. So we have actually colored our nodes so that we can easily identify them and associated edge weight and everything. And now I'm actually going to draw my graph, and here we have actually tries to show each green color that you see. You may not be seeing few of them because they are very low in degree, and that's why they are, if they are hidden behind the other edges, other nodes. And the green color is all the journals, and the red colors are all the authors. And you can see on the arc you have the weight that they carry. So if I have to zoom in on this, let's see if I can do. No, okay. Anyway, I can, so you can see it's 50. So and the color, so this is I did not put a legend here, but I can talk about this. Each arc color has a different color based upon the degrees that they hold. So if you go and see the code here, if my weight is greater than, less than or equal to 2, I'm using R. And if my weight is less than or equal to 695, I'm placing M. And this goes in this order so that if I meet this criteria, I'm R, then green, and then blue, and then maroon. So what does this mean? That, and so if color with maroon and blue, and then the green, and then R. So you can see this bigger chunk of the network or the subgraph you can see here. This is actually made up of a group of authors with the maroon, blue, and green, like the top highest edge value in the nodes, in our edge list. So this means that this is a very condensed and powerful set of people or the authors, and this is one of the journal that's citing all of them. And so this is a more powerful journal possibly. And then this is another journal here which is actually citing people with 112 edge weight, 165, 112, and 56, 56, 56. So this is like different types of edges edge weight that this journal is citing to the authors. Why? If you remember, I said if we drop edge value of 2, we would not be able to retrieve any information about the journal, because if you see there is, and the color red, so this is just only one color red that we can see in our whole network, and there is no other node with a different weight that's connecting to this. That is the reason if we drop this 2, we will lose the complete visibility of the journal that was actually citing here. So this is very this is not going to give us too much information about the whole network here or whole subgraph. So this different colors and the edge bits of the network, it makes it more easy to understand and easy to interpret the relation between the different nodes. And if we can see, let's what we have tried to find out is exactly what I just said, like the dropping of the weight hs2 will not make much difference into the network, and the graph with the high degree are mostly made up with the high degree of the edge weights that we saw very clearly here. And if we can break down this data set again, we can see that these 1, 2, 3, 4, 5, 6, so there are 6 different journals actually coming all together in this subgraphs. And can I count all of them? 1, 2, 3, 4, 5, and I'm sure there is one here which is very very low in the node size. So we have total 6, and if you remember we had total 16 uh, journals, and we have total 11 components. So 10 components are with the zero with just one journal in each, and the 11th component is with all the 6 journals in each. So maybe the group of people here, they are more powerful, and they are actually, or maybe they are relating to the topic that is being discussed. It looks like that's the reality here, because this is all talking about the and astro. I don't know about this Princeton, but yes, this looks like the journal of astrophysics, and something that relates back to the astronomical or astrophysics is actually citing the same, not same paper, but mostly related authors into the papers, and that author group has length of 306, and that can be I'll show you in a graph. So these are the different edges. Sorry, these are different journals that were cited, that were citing all those authors. It's like a very crisp version of only authors plotted together, and then we can see all the authors plotted together, and you can see this is the author maybe with the weight 2, this is 17 one, and this is the bigger chunk. So it is very clearly connected back to our main graph that we saw here, which is very clearly trying to tell how the network is actually structured within themselves. So that's all from our side, and we have tried to present our information in a way so that we can make sense out of the data. Only thing that we had concerned about the network size, we noticed that we had very less information about the more journals, and that is the one reason we could not find more islands in our network. But concept wise we were able to understand how this data is put together, and how you can understand the different depth and the connected components of the graph. Thank you so much.